Good morning. My name is Alison Ord. I have a small company called Mineral Dynamics, and I write and learn through the University of Western Australia. I also cycle. I'm a geologist, and I enjoy and worry about all aspects of the deformation of rocks. I'm particularly interested in the application of nonlinear dynamics to understanding how rocks deform. And in this presentation, I explore completely data-driven approaches to the analysis of mineralogical data from drill holes. The raw data must speak for themselves. My goal is to discover the underlying dynamics of the mineralizing system and the cross-correlations between mineral concentrations produced by the interconnected processes that developed a particular mineral system. I thoroughly enjoyed attending the Wolfram Summer School in 2019, and being inspired by Stephen, I think it would be truly great if exploring the behaviour of Rule 30 would result in much improved algorithms for exploring and predicting drill core data. So why do we drill anyway? The Minerals Council of Australia has this all worked out. They note in number 4 of their 30 things that more than 40 mined metals and rare earths are used to produce just one single smartphone. In the small print in the lower right-hand corner, it says that 1 ton of mobile phones yields more gold than 1 ton of gold ore. Everything comes from somewhere. If it didn't grow, it was mined. Our Earth is a finite resource. You might do better to work out how to improve recycling than to explore and mine our Earth, but please keep listening. The Welcome Stranger nugget, the largest ever found, weighed in at about 110 kilograms when discovered in 1869 in Victoria, Australia. The nugget is in the foreground in the sepia print on the top right, with those involved in its discovery. It shows more clearly as a golden fake on the left-hand side with a couple of diggers. The golden eagle is the largest nugget ever found in Western Australia, weighing in at about 32 kilograms in 1931, displayed in the lower 2 pictures by the boy who fell over it and his father. These guys were just plain lucky. So how do we explore today? Well, mostly still by luck and pragmatism. My 3 colleagues in the top photo, Mark Munro in the middle and Bruce Hobbs on the right, are looking out over the vast expanse of the West Australian bush with a salt flat behind them, worrying about that billion-dollar question: how do we predict the gold distribution? The middle picture is of Sunrise Dam just nearby. It's the 2nd largest gold deposit in Australia. The bottom of the pit is 760 metre deep here, and there is mining a further 1 kilometre underground. This used to be under a salt flat. And at the bottom is what we want to see in drill core: gold. Study of these systems has now entered the big data era, with more and more data collected at finer and finer scales. In the present era, where big data are generated routinely by mineral exploration companies, it is essential to have rigorous procedures for extracting quantitative information from these large data sets, for developing rigorous ways of prediction, both interpolation and extrapolation, and of deriving knowledge and understanding from such expensive data. Can Rule 30 provide such procedures? A dominant characteristic of mineralizing systems is the irregularity in patterns of alteration and of mineralization at all spatial scales, from thin section to regional scales. An important question is this irregularly purely stochastic, that is, the result of random processes, or are the underlying processes deterministic, understood here to be the result of well-defined chemical and physical processes? Is there information in this irregularity that gives us a better understanding of these deposits? The mineralizing systems are determined to be multiscale in nature with episodic histories. Strong interactions between processes operating at the various spatial scales produce ambiguous overprinting relations and paragenetic sequences, the sequential order in space and interpreted to be in time of mineral deposition in an ore deposit. What happens if we try to use some science to explore? As a first step, let's consider a mineralizing system to be a chemical reactor. This golden egg is our reaction vessel. It hosts the processes resulting in alteration and mineralization within the Earth's crust. We must have an open flow chemical reactor. This lower bluish box represents fractured rock, allowing for input of heat and fluid at the base of the system. Within the egg, a self-enhancing system of exothermic reactions results in alteration. Endothermic mineralization is initiated by higher temperatures. Heat and mass are lost out of the top of the egg as a result of advection and conduction. The size of the ore body is proportional to the input of heat and fluid. No wind, no fuel, no flames. These chemical reactors incorporate interactions between deformation, heat, fluid flow, and chemical reactions, as shown in this figure of dynamical nonlinear feedback processes. Modeling of such a system results in irregularity at all scales. The system appears to be random, although there is a hint of periodicity. Determinism, there's always some degree of prediction. Recurrence, similar states are revisited in both space and time. Chaotic transitions, one type of irregular behaviour switches to a different type of irregular behaviour. So where do we go for understanding? We consider a couple of templates for nonlinear dynamical behaviour, the Lorenz relationships which describe convection, whether it is of the Earth's mantle, fluid flow within the Earth's crust, or of the Earth's atmosphere, and the Rössler relationships used to describe chemical reactions. Convection in Earth's mantle, shown on the right-hand side, is equivalent to convection in a kettle. The outline of Africa is shown clearly in yellow. To the left of it is a sinuous red surface, near-surface mass, trailing north and northwest. This represents upwelling of hot material at the North Atlantic rise. Such Rayleigh-Bénard convection is well described by the Lorenz equations, the attractor for which is shown here, using Wolfram language. Similarly for the Rössler attractor as a descriptor for chemical reactions. Here is a Wolfram demonstration. Consider also the Scott-Gray relationships. We envisioned a regional array of chemical reactors, each representing an ore body. Such dynamical templates inspire SINDI, the sparse identification and nonlinear dynamics, described by Brunton and colleagues, for extracting the governing equations from data. So we have a model for a mineralizing system, which has as input various controlling factors. It has our golden egg as its focus, and from which we can contain output signals for, say, the mineralization, the host rock alteration, the vein and breccia infill. We think that orogenic gold systems should be analyzed as nonlinear dynamical systems. There is a suite of tools available to do this. The array of tools is quite large, but we have concentrated on recurrence plots, since recurrence is a fundamental property of dynamical systems. The use of such tools enables a range of quantitative measures and cross-correlations that are not otherwise obvious. On the left, we have 7 core trays containing cores of rock obtained from drilling down into the earth. Each bit of core is a metre long, and they are laid out top to toe. The colour reflects the chemical composition of white micas derived from near-infrared reflectance spectra of the core. We now have many kilometres of such data, providing detailed mineralogy and chemistry at millimetre and even micron resolution. On the right, the gold lode is noted to be associated with the blue or iron-poor white micas. Consider now, given the previous discussion, that the behaviour of a mineralizing system is described in the large dimensional state space with coordinates comprising the state variables: fluid velocity, fluid pressure, temperature, strain rate, and the rates of the N chemical reactions in the system. A drill hole spatial data series for, say, gold concentration is a projection from the large dimensional state space onto a one-dimensional spatial series, the drill hole. The drill hole mineralogical signals we observe are the projections from a space defined by these space variables onto a single drill hole record that we observe at a particular place as a one-dimensional spatial series. The Takens theorem states that the complete dynamics of such systems may be encapsulated in a data series for a single state variable collected through that system. The reason for this, as expressed in the mineralising system above, is that in systems where all the state variables are coupled, the behaviour of one depends on the behaviours of all the others, and so the data series for one variable has the behaviours of the other variables encoded within it. Consequences: that the attractor constructed from a spatial delay embedding of information from a single line of data collected through a mineralising system should represent the entire mineralising system. Working through this, here is a plot of log gold concentration down a drill hole. Left top, right bottom. Here also is a plot of chlorite abundance similarly down a drill hole. How do we measure their irregularity? Recurrence plots visualize the trajectories of system states in phase space and the probability that given states recur within a given margin. The top row summarizes the previous discussion. Coupled sets of nonlinear processes lead to chaotic behavior in space and time. The behavior of such systems can be represented by an attractor that is a plot of all possible states of the system. Recurrence here is shown as two dots close to each other, within a radius-defined volume on, in this case, the Lorenz attractor. Such recurrence is black in the plot on the right, describing the behavior of the system for given embedding dimension and lag. The bottom row starts with the colored distance map, followed by the recurrence map, plotting a recurrence within the prescribed radius. The lengths of the diagonal lines are a measure of predictability. The recurrence plot can be converted to a recurrence network that mimics the attractor for the system. Here, a crude version of the Lorenz attractor is obtained. So we start exploring recurrence plots for drill core data. On the top left, the plots say that the distributions are not the result of random processes. There's strong laminarity, the vertical and horizontal lines in both. This is evidence of many chaotic transitions. Each plot supplies a fingerprint or DNA for the ore body. On the top right, we compare gold with cerussite and note windows of similar behavior. Beneath this on the left, we note strong correlations between gold occurrence and chaotic transitions in cerussite. And on the bottom right, we ask what these transitions might represent with a mineralizing chemical reactor. To what extent might we be able to map these transitions? And now to Rule 30. As Stephen Wolfram says, the setup for Rule 30 is extremely simple. One's dealing with a sequence of lines of black and white cells. Given a particular line of black and white cells, the colors of the cells on the line below are determined by looking at each cell and its immediate neighbors and applying a simple rule. I drill the result for comparison with the drill core described above and explore the behavior of the central column. It's a cellular automaton. It has no physics associated with it. It certainly has no partial differential equations associated with it. I can't build a dam wall with it, as far as I know. However, there I was at the Wolfram Summer School. I was working on recurrence quantification analysis in Wolfram language with Phillips for application to geological data. And I heard of Rule 30. So why not go through the same analysis for Rule 30? Here are a few results. On the left are data from a drill core, and on the right from Rule 30, 11,864 points in each case. Here are the 3D spatial attractors for the two sets of data. What is particularly stunning is not that they appear different, but that there is a clear attractor for Rule 30 at all. There's no clear attractor for white noise. Increase the embedding dimension for white noise and the attractor continues to fill space. This attractor does look much like those I have derived from folded rocks, with recurrence, but not perfect periodicity. These distance maps are derived from the data using Phillips's Wolfram language code from last year. That for the drill core shows both diagonal lines representing determinism, the predictability of the system, and horizontal and vertical lines representing phase transitions, the intermittency on the system. Rule 30 also displays such characteristics. Indeed, at a first glance, diagonal lines dominate the pattern more than for the drill core. We're going to zoom now into windows within these figures, each window 200 points wide, and succeeding windows displaced by 150 points from bottom left to top right up the leading diagonal. Look at the richness of the detail, the variations in the behaviour. For Rule 30, at least as much as for the drill core. It's all very exotic and provides wonderful visuals for t-shirts and tablecloths and rugs. But we need quantitative measures for this behaviour, and Weber and Marwan and colleagues have provided these over the years. The next slides will show results for these measures. Recurrence rate, recurrent points falling within a given radius for the number of points in the signal. Determinism, recurrent points forming diagonal line structures, predictability of the system. Laminarity, recurrent points forming vertical line structures, intermittency of the system. Trapping time, average length of vertical line structures, the length of time or space the system remains in a specific state. Trend, a measure of system stationarity. Entropy, the Shannon information entropy of probability distribution of the diagonal line lengths, complexity of deterministic structures. And chaos, 1 over the length of the longest diagonal line, interpreted to be equivalent to the maximum Lyapunov exponent of the system. The lower the value, the more predictable the system. And here are those results. Recurrence, determinism, laminarity, trapping time, trend, entropy, chaos. At first glance, the only obvious difference is the constant nature of chaos for Rule 30. The magnitudes of all the measures are crudely similar. Here are the same results. This time I look for possible similarities or opposites in the patterns. The green lines for the drill core pick out minima in all measures at about the same points. I found the task a bit harder for the Rule 30 data, and the purple lines are the result. In summary, I found it difficult to distinguish data created by Rule 30 from these data for the abundance of some element collected progressively down a drill core. The main difference to date is that Rule 30 data reflect just one Lyapunov exponent rather than the variability represented by drill core data. 2 different pieces of software were used to explore this curiosity, using different embedding dimensions and lags and other variables used in recurrence quantification analysis. Same results. Conclusions. Analysis using recurrence plots shows that the apparently irregular data sets of mineral composition and abundance from the Sunrise Dam orogenic gold system are indeed the result of deterministic processes operating within a nonlinear dynamical system. Although the dynamical attractor for this system is difficult to define, nonlinear prediction indicates that the embedding dimension for the attractor is in the range 7 to 10, so that the number of coupled physical chemical processes that operated to produce the system is in this range also. The entropy and first Lyapunov exponent for this system are relatively small, meaning that the information content of these data sets is large and that prediction over useful ranges is possible. It's uncanny the extent to which the analysis for Rule 30 might be inferred to have similar interpretation. In the present big data environment, where huge data sets are routinely collected in the minerals industry, it is important to extract as much knowledge from such data as possible. So remind yourself of our central questions. Are the apparently irregular data sets obtained from drill core of whatever data stochastic, the result of random processes, or deterministic, the result of well-defined physical and chemical processes? Is there information in these irregular data sets that gives us insight into the mineralizing process? Recurrence analysis is a method for rapidly extracting knowledge from these large, expensive data sets and for providing fingerprints to characterize quantitatively and compare data sets. Do you have any better ideas? Thank you for listening. Please let me know if you have any questions. Here is our bibliography, which may answer some of them.